Hello again. My Overwatch match got cancelled, so here I am. Just one thing, as the user Felix Nielsen pointed out in the comments, I forgot to mention that calloc is actually very special compared to Malloc. Calloc zeroes out the memory, so you can think of it like this. If I were to use Malloc, I would have a lazy paper man who would just go and pick up some pieces of paper out of the trash. Of course, these papers may or may not have already been used, so sometimes you'll get blank pieces of paper, sometimes you'll get pieces of paper that have been scribbled on. Which is important to note because you almost always want paper that is blank and has not already been scribbled on or crumpled or what have you. So if I were to use Malloc, a few things would change here. First, it only takes one argument, where you do this, and you multiply it yourself. So this tells the paperman, please get a 3x4 sheet, or a rows by columns sheet of that can fit this many characters. Or rather, this many characters. A sheet that can fit this many characters. So let's say this is 3, this is 4, it needs to fit 12 characters. So, if we were to do this, we would get trash. In fact, I can actually show that to you right now. Is that if I were to do that, I'm just going to copy this over really quick. And I'm going to open up Bash. Also, if you guys need help installing Ming, as I talked about in the previous video, I will actually make a quick tutorial video on that because sometimes it can get a little confusing and I've had my fair share of frustrations with it. But for now, I will just use Bash. That's because I'm on the Windows Home Insider Preview and I can just do things like that because I'm special. Anyway, so let's GCC WL, make sure this is saved. C equals C99, example.c. I'll shut you 8 out, 3 and 4. That's actually very interesting. That shouldn't have worked. Well, it appears as though Windows is being a little too nice to me today. Or maybe I could do this and try it out really quick. Yes. Alright, so it looks like the paperman is just being nice today. He's decided that he's not going to be lazy and he's actually going to give us memory that isn't full of crap. But do be aware that the chances of this being zeroed out and all pretty like this is very, very low. So assuming this was full of junk, how you would fix this is you would do something called, if you didn't want to use calloc for whatever reason, you would use a macro called zero memory. And it does exactly what you would think it would do. Zero memory, simulation, and then the length. And this basically does the exact same thing as calloc does. But for now, I'm just going to use calloc because I see no point in using Malloc yet. So just let me open up my notes again. So what we're going to do right now is we're going to set up the simulation. We're going to seed it with a random sort of thing. So for now, we're not going to use any borders like I showed you in a few videos ago. But instead, we are going to create a function called create simulation, which I'm going to shorten down to create for now. Int rows, int columns. That's all we need. This is going to return a matrix. Sorry, by matrix I mean memory, representing the simulation. But it's also going to do a few other things for us, which I'll get to now. And you'll notice that it is returning a pointer to characters, much like we did here. So I'm actually going to have to move all of this out. Char start, create int rows, int columns. And then we're going to allocate our memory. But we're also going to do a few more things to it. For one, we're going to seed it with a randomly with live cells and dead cells. Because for the ease of display, we're going to represent the alive cells by a £sign and the dead cells by a period. And this is actually fairly simple. It's much like we did when we were printing out int y equals 0, y is less than rows, y plus plus, for int x is equal to 0, x is less than columns, x plus plus. And then we're going to use random numbers. But the important part is we're going to get a random decimal number. Decimal numbers are not integers, so we can't use the typical rand as we normally would if we wanted a random integer. So what we're going to do is we're going to create a special function, our own function, that gets a random float. And we're going to name it that, or random double. Double get random double in range, double minimum, meaning the minimum number we want it to be, double max, meaning the maximum number that it can be. So it's going to, so let's say this is 3 and this is 5, it will only get numbers with decimals between 3 and 5. Alright, so again, I assume you're familiar with programming, but a double is higher precision, meaning you get more decimal points. A float has like 5 or something like that. But it's a lot more complicated than that, but just for now, just use a double. So we're going to write that double function really quick. In fact, I'm actually going to write it right here, because I feel as though you're supposed to declare it before you use it. Double min, double max. Now, this is a little bit fancy, but we're going to cast rand. Like I said, it gets a random integer, but instead of an integer, we're going to cast it to a double. So if this is like 30, it's going to be 30.000000000. But then we're going to do something interesting to it. We're going to divide it by rand max. This is the highest number that rand can be. By dividing this number by rand max, we are getting a random decimal point. So let's say this was 30. This would divide by max, and it'd be like 0.000018 or something like that. Well, that's all well and good if we want a small random number. But in fact, we want to multiply it by max minus minimum. So that, again, this is the difference between the two, meaning if this was 4 and this was 2, the answer would be 2. I can't really remember why we do that. It's just the way we do things. And then in order to get your minimum, you just add your minimum. This makes sure that it will always be at least the minimum. And this makes sure that so this makes sure that it's only within max minus min above min. Meaning if this was like 5 and this was 2, this would be 3. So it can only be 3 within 3 of 2, so that it doesn't hit 5. And that's it. We just return it. So this is how we get a random number. Random decimal, sorry. So why did we just do that? Well, later on we're going to allow the user to provide a number between 0, or at least it has to be above 0, and 1. And that's going to be the chance that a cell is alive or dead. Meaning if they selected 0.35, there would be a 35% chance that a cell would be alive. So let's seed that really quick. Just give me a second, sorry. Alright, so if get random float in range, we want it between 0 and 1, is less than or equal to, we're just going to seed it with 0.35 for now. So this makes sure that it's at least a 35% chance. Yeah, so basically this means it's going to be at least a 35% chance that a cell is alive. Or that it is a 35% chance that a cell is alive. So, if it is alive, then we're going to say what's at simulation plus y times columns plus x, much like we did in the previous video. And then we're going to represent it by a pound symbol. And if not, we're going to seed it with a dead cell, which is represented by a period. Now, you can choose actually anything that you want between these two. It's just I prefer pound and period because it provides a very high level of contrast between live and dead. So now that we've accomplished that, we can now return our simulation. So inside of begin simulation, we're going to say jar simulation is equal to create simulation, or create, sorry, rows, columns. And this is where you're supposed to check whether or not the operating system actually had memory for you. So if simulation is equal to null, return null. Because if this was null, this would cause an exception because we're trying to write in memory that's not ours. Null basically means that it doesn't exist. So if we try to allocate memory, the memory doesn't exist, we just say that it doesn't exist. So if simulation is equal to null, return, and this means just exit out. So, okay, we can keep typing out the for int y stuff like this to print out the simulation every time, or we can create another small helping function called display. So let's do that really quick. Void display, and then we're going to have to pass it rows and columns as well, but we also have to pass it the simulation. So the reason we need rows and columns is to tell the display function what it should look like. So it's like, okay, there's 3 rows and 4 columns. Okay, each line I will begin after doing 4 columns. Alright, so we've got our simulation here, and now for our display simulation, which we should put above begin. Sorry about that, I forgot to put my int here. And then char star simulation. And we're basically going to do the same thing that we've always done. First, actually we're going to say printf \n, 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 \n. You can put as many here as you want. But basically we just want to clear the screens so that we're not looking at our old simulation right next to the new simulation. So we're just going to iterate over them like usual for int y. You can see why this would get repetitive after a while, and why it's a good idea to alleviate this so it's not as much work on you. So what do we use to display a character? %c. And then I'm going to put a space there because it helps because the console only has a funky aspect ratio, we're compensating for that. So instead of like having it all clumped together in like a weird rectangle, we're going to try to make it as square as possible. And then the same thing that we kept doing, simulation plus y times columns plus x. And then here, we're going to print a new line because this is the end of a row. Alright, and then we're going to add some other goodies here later, like the current generation. But that'll probably be in a different video since it goes over static variables. Alright, so now that we've got our simulation, we're now going to display rows, columns, simulation. And that should be it. So if we compile it, oh, I forgot the F. Yeah, it's right here. Oops. There we go. Forgot to save it. That can get a little annoying sometimes, so you should always save before you attempt to compile. There we go. Let's say I want, 10 rows, 20 columns. Ta-da! And here's the beginning of our simulation. This is our seeded simulation. You'll notice that about 35% of the cells are filled with live cells and dead cells. So that's probably all I'm going to do for this video for now. Yeah, because it actually gets really complicated once you get into counting the neighborhoods. And oh shoot, I'm sorry guys. You're actually supposed to do rows plus equals 2 and columns plus equals 2. Now I'll explain why. So with our memory, we have a graph. Well, as it turns out, it's actually very, very difficult to wrap around. So we use a little bit of a cheat. So normally, if we didn't do the plus equals 2, we would get something that looks like this. It looks like this. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So let's say this is our 4x4 grid. So if we wanted to get a character, so let's say we hit the end here, and now we need to count the neighborhood. Well, as it turns out, we can't count above or to the side or to the top right of this cell because there's nothing there. And as it turns out, it's actually very difficult to build a formula that compensates for this. So it says, okay, now I'm counting to the right of 4. Let's just go to 1. Believe me, I have tried several times. And creating like a mathematical formula to find this number when you're at the end of here, it's very, very difficult. So instead, what we do is we wrap our grid with extra cells, invisible cells that we don't display. So let's wrap that around really quick. So this is the plus equals 2 because we're adding an extra row, and 2 extra columns. So instead of having to do a bunch of complicated math, we can simply just iterate through the inside of the visible cells, and then just copy this cell into here, and this cell into here, and vice versa. Like this cell would go to the bottom, this cell would go to the top. And by that way, we can cheat and not have to worry about accessing memory that's not ours or creating an obnoxious formula to solve that. So that's why that plus equals 2 is here. In order to compensate for this, so that we don't display that invisible data, we do this. So when we display, we say y is equal to 1, x is equal to 1, rows is equal to minus 1, columns is equal to minus 1. Notice how this gets rid of the first row, and this gets rid of the last row. This gets rid of the first column. This gets rid of the last column. This gets rid of the last column. So that we only iterate within our visible bounds. Now don't forget to do it here as well, so that we're not randomly seeding cells that we don't need to. And if we compile, it should work exactly as it did before. Yep. Notice how we don't have extra rows or extra columns. In fact, I'll even change this to something smaller so that you can actually see. See? 2 rows, 4 columns. So we don't have all of this annoying border. So that we don't have to deal with that. So that's a way of like cheating the system, so you don't have to do like a bunch of annoying math. And believe me, it is a total pain. I've tried it several times in older projects, but it just never works out quite the way you'd expect. So that should be it for now. I'm probably going to create a video right after this one that goes into counting the neighborhood. And I just have to figure out a way to visually show that to you. But the long and short of it is it's hard to just show you counting the neighborhood. So I'm probably just going to end up printing out the number of cells next to each cell at index like 00, 03, etc. So that's it for now, and I will start thinking about how to do my next one. Have a fantastic day. Like, subscribe, do whatever you want.